Welcome to the foundational overview of the Aurion Gravity Frame AGF-1R and the revolutionary Refractive Vacuum Gravity RVG theory. Unlike conventional gravity models that rely on mass or spacetime curvature, RVG proposes that gravity can be engineered by modulating the refractive index of the quantum vacuum. This programmable approach allows for tunable, reversible, and vectorized gravity effects, opening the door to propulsion systems that are massless, silent, and inertia-free. The AGF-1R integrates 5 primary systems: RVG field generation, quantum AI control, metamaterial hull, plasma stabilization, and navigation and vectoring, each working in concert to realize this new paradigm. Let's explore why this system is not just theoretical, but a compelling subject for advanced scientific study. Casimir plate modulation chamber is the heart of the RVG field generation system. It leverages the Casimir effect, where vacuum energy density is altered between two closely spaced conductive plates. In the AGF-1R, this principle is extended. Plate geometry is programmable, spacing is dynamically adjusted by AI, and the resulting field output is vectorized through refractive slope shaping. Subsystem converts quantum geometry into usable thrust, forming the basis for gravity-like field generation without reliance on traditional mass. The chamber's mathematical model describes how the refractive slope and plate geometry combine to produce a directed gravity flux, a concept that is both novel and experimentally approachable. Encapsulating the Casimir chamber, the diamagnetic boundary shell uses advanced materials to guide and contain the refractive gradient. Diamagnetic materials repel magnetic fields and stabilize the refractive slope, acting as a boundary layer between the modulated vacuum and ambient space. This shell prevents decoherence and field leakage, ensuring that the gravity-like vectors generated are coherent and precisely directed. The mathematical model for this subsystem demonstrates how diamagnetic field shaping and refractive gradients interact, providing a robust framework for experimental validation and further study. ZPE harvesting core is responsible for extracting and regulating quantum vacuum energy, providing a continuous non-reactive power source for all RVG field operations. Using quantum coupling nodes and oscillatory field traps, the system captures zero-point energy fluctuations and routes them to the Casimir chamber and diamagnetic shell. The mathematical model quantifies the energy extraction process, making it a fertile ground for both theoretical and applied research. This subsystem's ability to harness vacuum energy is a major leap forward, offering a sustainable solution for advanced propulsion. Entanglement feedback matrix maintains quantum coherence and synchronization across all RVG field generators. By embedding entangled qubit arrays in each subsystem, the AGF-1R achieves real-time, latency-free feedback and control. The AI core interprets entanglement correlations and dynamically adjusts field parameters, ensuring stable and adaptive gravity modulation. This approach leverages quantum information science, making the system highly resilient and responsive, qualities essential for advanced aerospace applications. At the core of the quantum AI control system, the adaptive field logic processor translates mission parameters and environmental data into real-time adjustments of the RVG field geometry. Using a quantum-optimized neural lattice, it calculates optimal refractive index profiles and modulates subsystem parameters for thrust, stealth, and maneuvering. This subsystem exemplifies the fusion of AI and quantum physics, enabling the AGF-1R to adapt instantly to changing conditions and mission requirements. Refractive conduit layer forms the primary transmission surface for RVG field propagation across the vehicle's hull. Composed of engineered materials, this layer ensures that the refractive slope remains continuous, preserving field integrity and enabling stealth operation. The conduit mesh routing nodes and coherent stabilizers work together to guide field vectors without loss or decoherence, making this subsystem vital for both performance and survivability. To maintain stealth and operational efficiency, the thermal nullification matrix absorbs and redirects heat generated by RVG operations. Using quantum tunneling channels and infrared cancellation mesh, this subsystem prevents external thermal emissions and maintains hull temperature equilibrium. The integration of advanced materials and quantum heat dissipation techniques ensures that the AGF-1R remains undetectable to infrared sensors, a critical advantage for both military and scientific missions. Ionized vacuum buffer creates a stabilized plasma interface between the modulated vacuum and ambient space. This dynamic sheath absorbs quantum noise and environmental interference, maintaining field integrity during high-velocity maneuvers. The buffer's adaptive design with A-controlled plasma density regulators and quantum noise absorbers ensures that RVG fields remain coherent even under extreme conditions, making it indispensable for advanced aerospace application. Oscillation dampers are critical for suppressing unwanted quantum and electromagnetic oscillations within RVG field zones. By employing quantum phase inverters and electromagnetic absorption mesh, this subsystem neutralizes disruptive waveforms and preserves the integrity of refractive gradients. The AI damping controller continuously refines phase offsets, ensuring field stability and coherence even in dynamic or hostile environment. Gravity Vector Shaper translates refractive gradients into precise propulsion vectors, enabling full control of thrust, orientation, and maneuverability. Using tensor field mapping and AI-driven amplification nodes, this subsystem allows the AGF-1R to maneuver with zero inertia lag and full directional control. The mathematical model for vector mapping provides a clear path for experimental validation and optimization. Inertial override grid cancels inertial forces experienced by crew and onboard systems during RVG maneuvers. By generating inverse refractive fields, the subsystem creates a zero-net force envelope, enabling high-velocity travel without G-force trauma or structural stress. The integration of AI override controllers and structural stress dampers ensures both crew safety and vehicle integrity, making this technology a cornerstone for future aerospace design. AGF-1R's scrollable subsystem archive provides a comprehensive modular breakdown of each core and supporting system. This format allows researchers, engineers, and students to explore the architecture in detail, subsystem by subsystem. Each entry includes labeled schematics, operational logic, and mathematical models, making the archive an invaluable resource for both theoretical study and practical engineering. The modularity and clarity of this archive are designed to facilitate cross-disciplinary collaboration and rapid innovation. AGF-1R system and RVG theory present a compelling case for advanced academic study, including at the MIT level. First, the use of programmable refractive index modulation as a basis for gravity is a testable hypothesis that extends quantum field theory in metamaterial science. Second, the integration of quantum AI control and entanglement feedback aligns with current trends in quantum information and adaptive systems. Third, the modular ceremony-free engineering approach ensures operational clarity and reproducibility. Finally, the system's reliance on established phenomena like the Casimir effect and diamagnetic field shaping grounds it in experimentally accessible physics, making it ripe for both theoretical exploration and laboratory validation. Adapting the AGF-1R system for a large lenticular, saucer-shaped, aerospace vehicle is both feasible and advantageous. The saucer geometry naturally supports the distribution of refractive gradients and plasma buffers, allowing for omnidirectional vectoring and enhanced stability. The modular RVG subsystems can be scaled and arrayed around the lenticular hull, with the quantum AI core orchestrating field generation and navigation. This configuration maximizes stealth, maneuverability, and inertial override capabilities, making it ideal for both atmospheric and deep space missions. The lenticular form also facilitates efficient heat dissipation and field containment, further enhancing operational performance. Key assumption of RVG theory is that the vacuum is not empty, but a tunable medium with a variable refractive index. This property can be shaped via electromagnetic, quantum, or exotic field inputs, allowing for the emergence of gravity-like effects independent of mass. This concept challenges traditional views and opens new avenues for research in quantum field manipulation, metamaterials, and advanced propulsion. The ability to engineer the vacuum itself is a transformative idea, with implications for both fundamental physics and applied technology. The RVG framework, gravity is not an inherent property of mass, but an emergent phenomenon resulting from controlled refractive slopes across spatial regions. By shaping the refractive index gradient, gravity can be generated, reversed, or nullified. This mass-independent approach allows for the creation of gravity-like fields in environments where traditional propulsion is impossible, such as deep space. The implications for spacecraft design and interstellar travel are profound, as it enables new forms of maneuvering and energy efficiency. Integration of quantum AI modules throughout the AGF-1R system is a hallmark of its advanced design. These modules interpret environmental data, mission parameters, and entanglement feedback to dynamically adjust field parameters. The result is a system that is not only adaptive and resilient, but also capable of learning and optimizing its performance over time. This AI-driven approach is essential for managing the complexity of programmable gravity and ensuring safe, efficient operation in unpredictable environments. Casimir effect, a well-documented quantum phenomenon, serves as the experimental precedent for RVG field generation. By manipulating the geometry and spacing of conductive plates, the AGF-1R system alters vacuum energy density and creates programmable refractive gradients. This direct link to established physics provides a solid foundation for further research and experimental validation, making the RVG approach both credible and innovative. Time crystal oscillation is proposed as a method for stabilizing refractive gradients over time, enabling persistent gravity fields. Time crystals are a new phase of matter that exhibit periodic motion without energy input, making them ideal for maintaining the coherence of RVG fields. This hypothesis, while speculative, is grounded in recent advances in condensed matter physics and offers a promising avenue for future research and development. Magnetic composites are essential for shaping field boundaries without introducing mass. These materials, such as bismuth titanium alloys, repel magnetic fields and stabilize the refractive slope, ensuring that RVG fields remain coherent and precisely directed. The use of advanced composites is a key enabler for both stealth and efficiency, making them a critical component of the AGF-1R's architecture. Zero-point energy, ZPE extraction is at the core of the AGF-1R's power system. By harnessing the omnipresent energy of the vacuum, the system achieves continuous non-reactive propulsion. The mathematical model for ZPE extraction is based on quantum field theory and is supported by experimental evidence from Casimir effect studies. This approach offers a sustainable and scalable solution for future aerospace and energy applications. AGF-1R's AI-driven optimization core continuously refines field parameters based on real-time feedback from sensors and mission interfaces. This adaptive approach ensures that the system operates at peak efficiency, regardless of environmental conditions or mission demands. The use of machine learning and quantum logic gates represents the cutting edge of control systems engineering, making the AGF-1R a model for future intelligent vehicles. Stealth is a critical requirement for both military and scientific missions. The AGF-1R achieves this through a combination of metamaterial hull design, thermal nullification matrix, and quantum tunneling channels. These technologies work together to absorb and redirect heat, cancel infrared emissions, and maintain hull temperature equilibrium. The result is a vehicle that is virtually invisible to conventional detection methods, setting a new standard for operational security. Plasma stabilization is essential for maintaining the coherence of RVG fields during high-velocity maneuvers. The ionized vacuum buffer and oscillation dampers work in tandem to absorb quantum noise, suppress electromagnetic interference, and preserve field geometry. This subsystem's adaptive design ensures that the AGF-1R can operate reliably in even the most challenging environments, from deep space to planetary atmosphere. The ability to program gravity vectors is a defining feature of the AGF-1R system. By mapping refractive gradients to propulsion vectors, the vehicle achieves full control over thrust, orientation, and maneuverability. This programmable approach is supported by tensor field mapping and AI-driven amplification nodes, providing a robust framework for both theoretical study and practical application. Inertia cancellation is achieved by generating inverse refractive fields that counteract acceleration effects. The inertial override grid creates a zero-net force envelope around the crew and sensitive systems, enabling high-velocity travel without G-force trauma or structural stress. This technology not only enhances crew safety but also expands the operational envelope of the vehicle, making extreme maneuvers possible. AGF-1R's modular system design allows for rapid reconfiguration, scalability, and cross-disciplinary integration. Each subsystem operates independently but contributes to the unified operation of the vehicle. This approach facilitates maintenance, upgrades, and adaptation to new mission profiles, making the AGF-1R a flexible platform for future research and development. RVG theory and AGF-1R system represent a post-Einsteinian approach to gravity and propulsion. By treating gravity as a programmable, emergent phenomenon rather than a fixed universal force, this new science blends quantum field theory, metamaterial engineering, and AI-driven control logic. The result is a framework that is both operationally focused and theoretically expansive, inviting further exploration and innovation. AGF-1R and RVG theory open new frontiers for research, collaboration, and technological advancement. By providing a modular, testable, and scalable platform, the system invites participation from physicists, engineers, AI specialists, and material scientists. The potential applications range from deep space exploration to next-generation aerospace vehicles, making the AGF-1R a catalyst for interdisciplinary innovation and discovery.